Okay, good afternoon, everybody. Thank you, Bob, for inviting me to make this presentation about validation principles of land products. So, I will start my presentation by a brief introduction, going from generic definitions of validation towards specific land variable issues. So I will focus mainly in this presentation on soil moisture and leaf area index variables. This morning we had a presentation dealing about snow, so let's switch here to soil and vegetation. So I will show some examples based on the use of in situ observations to do the validation of satellite products, and then I will switch to the use of model simulations. And in a fourth part, I will talk about the synergies between satellite Earth observation data, in situ data, and model simulations. Then I will try to introduce briefly the concept of multiple triple collocation, and I will show to what extent data simulation can contribute to the validation of Earth observation land variables. So let's start with the introduction and a number of definitions. So if you go on Wikipedia, it's often very useful to go on Wikipedia. You will find a very generic definition of validation, which is applicable to any industrial process or to any production process. So, in fact, we have to make the difference between verification and validation. These two activities are different. So, validation is a process very much related to external users, while verification is something which is embedded into the production process, and in general it is an internal process. Well, in the field of Earth observation, both validation and verification require a very solid technical background, and very often the same persons or the same group do validation and verification. This is why, in general, in Earth observation, the community does not really make the difference between the two, and we talk about validation in general, and the definition here is independent assessment of the quality. So the specific features here are that in Earth observation we make the difference between direct validation and indirect validation. So direct validation is based on completely independent data, for example, in situ data. And indirect validation is based on the comparison of a new product with other pre-existing products, either derived from satellites or from models. And then there is the concept of scientific validation, meaning that for new products, the results are published, for example, in the open peer-reviewed literature, using standard methods and scores. Then, regarding land variables, a number of international initiatives exist today. So in the framework of the CEO's working group on calibration and validation, there is now a land product validation subgroup, which has issued a number of reports and recommendations. In the framework of GEO, there is a QA4EO initiative, which is aiming at specifying quality indicators and working towards a standardization effort. And in Europe, as you know, there is the ESA Calvet activities, and also the ESA CCI projects, which were mentioned this morning. UMETSAT has the satellite application facilities, and in the framework of Copernicus, there is a number of FP7 projects related to land variables, So there was GeoLand 2, which is finished now. There is the Imagines project, and there is us, CORECLIMAX. And of course, there is the Copernicus Global Land Service, which is operational and which has a validation component. So regarding land time series, we have to face a number of specific requirements. So regarding ECV, we have to deal with long time series, and in general, with long time series, direct validation. So direct validation, of course, is needed, but it's difficult because in situ observations are limited in space and time. So on the right, you have a snapshot of a weather station, automatic weather station of Météo France in southwestern France, and so you see some instrumentation of the weather station, and then here there is a small plot in the weather station where soil moisture probes and soil temperature probes are buried in the soil. So of course this kind of measurement is very, very local. This is why, again, these in-situ data are very much limited in space and time, and direct validation using in-situ data is very limited in space and time. This is why we need also indirect validation based on product intercomparison, on comparison with models, and also based on the integration of the satellite products into models through data assimilation and reanalysis. This was mentioned a little bit yesterday. Reanalysis have also a role to play in the validation of the upstream satellite products. So now there is a number of specific issues over land. So here you see a figure derived from Google Maps. Again, it is in southwestern France. So there is a mixture of forests, croplands, areas, and for example, in southwestern France, we always have a mixture of bare soil and crops or grasslands and so on. So we have to face very complex landscapes. So yes, we have to face a large variety of scales in relation to surface heterogeneity, but also we have to face a large variability of and a large variety of applications and requirements, and also of methods. This is why over land the maturity of the validation is probably less than in the field of atmospheric variables and ocean variables. And so far the use of biophysical variables is often limited to research applications. Nevertheless, operational services start to emerge in relation to drought monitoring or agriculture monitoring. So, the land product validation subgroup I was talking about from CEOS has issued, as I said, a number of recommendations. So regarding validation, and this is related to the maturity matrix which was mentioned this morning, several stages are separated. So the first stage is a basic validation using a limited set of in situ sites. Then a second step uses a more extensive data set, and also the spatial and temporal consistency of the product is checked using similar products or pre-existing products. And this is done at a global scale, and again, this is scientific validation. The results are published in the peer-reviewed literature. Then there is stage 3, where the uncertainties are characterized in a better way, in a sufficient number of locations and time periods representing global conditions. And then the stage 4 consists in repeating all this once a new version of the product is available. So I will show now a number of examples related to surface soil moisture and the leaf-area index. So for surface soil moisture, as I said, as you could see on the snapshot, well, we have to bury this kind of soil moisture probe. This is a capacitance probe into the soil, and well, in fact, this sensitive part of the instrument is only 6 centimeters. So what you see is very limited in space, of course. So it's very local. In spite of that, an effort was made to gather this kind of in situ observations at a global scale, and now we have an international soil moisture network gathering this kind of information. So you can see here a map with the stations. So most of them are located in the USA and in the former USSR. And in the former USSR, most of the stations are no longer active. Right? It's an historical data set. And in Europe, we have some stations in southwestern France. So this network is operated by Météo France. So you've seen an example on the snapshot. In Italy, Germany, Spain, well, and also in Denmark. So this figure shows a time series of surface soil moisture. So these are measurements at a depth of 5 centimeters, and each color represents a different year. So the time series starts in 2007 and continues in 2014. So you can see that there is an annual cycle, of course, with the lowest values observed at summertime. But there is also a very large day-to-day variability related to the precipitation regime and to the evaporation. So as this shows that this absolute, well, what is shown here is an absolute value in cubic meters per cubic meters, and it is extremely variable in space and time. So well, all this is very local, and these local relative temporal changes are affected by representativeness error. So when you compare a satellite product with such observations, you get an estimate of the error of the satellite product, but also of the uncertainties in the in situ observations, and an additional error related to the representativeness. Well, this representativeness error may change from one season to another. For example, here you can see time series of surface soil moisture over a set of 12 stations in southwestern France in a period in 2007, which is rather wet, with a high number of rainfall episodes. And in spite of the stations being on average separated by 40 kilometers, you can see that there is a high consistency in the time series from one station to another, because at this period of the year we had a lot of stratiform precipitation. So basically the time series are consistent to a large extent from one station to another. On the other hand, in a dry period, this was in May-October 2012, you can see that what is observed in one station can be different, completely different from what is observed in a neighboring station. So, well, we've seen that surface soil moisture has a seasonal cycle. But to some extent, getting the seasonal cycle right in a satellite product is something which is rather trivial. And also, getting the seasonal cycle right is not a proof that your satellite product is really related to the physics of soil moisture. So what we need to check is that the day-to-day variability of surface soil moisture, which is related to the precipitation regime, but also to soil evaporation, is consistent. And to do that, a technique which is often used in climatology is to work with scaled anomalies. well, the scaled anomalies are defined in such a way, in this way. So you consider a given window of time. Over this temporal window, you compute the standard deviation of the surface of moisture, the mean, and then you divide the distance to the mean by the standard deviation. So in order to eliminate the seasonal cycle, you can use a gliding window. So for surface of moisture, a good size of the gliding window is about 1 month, 5 weeks. And you calculate this quantity yes, from one day in the year to another. And this figure represents what you obtain for a given station in southwestern France. So in black you see the in situ observation of the scaled anomaly. In red you see what is obtained from the ASCAT wind scatterometer, which overland provides information about surface of moisture. And in blue you see what is derived from the SMOS satellite. And by the way, you can see that at least for some events, the consistency between the three estimates is remarkable. So, if now we try to compare the scores in terms of correlation between SMOS and in situ observations, ASCAT and in situ observations, this is what we get. So when we look at absolute values, well, it's difficult to make the difference between the two products. But when we look at scaled anomalies, this comparison clearly shows that better results are obtained with one product, which is ASCAT, which is more mature, which has more maturity than the SMOS products. What I'm showing here consists of the very first SMOS products in 2010. So this was for surface of moisture. Now let's switch to leaf area index. So here the technique is to cut vegetation. So through destructive measurements. So in general, you harvest 1 square meters of product samples, and the leaf surface is digitized using a planimeter. Another way to do this kind of measurements is to use an instrument called LAI 2000. So you measure the incoming solar radiation above and below the vegetation canopy. Then, the way to go from these very local measurements to global validation is the following. So we have our individual measurements, so either destructive or LAI 2000. Then we consider elementary sampling units, ESU. In each unit, you do the average of 10 to 100 measurements. And then, over a given site, you consider 20 to 100 ESUs. And you aggregate the ESUs using a transfer function based on satellite high-resolution images. And in this way, using 50 to 100 sites, you can try to start validating your remote sensing products. So, for example, this is what is obtained in the Belmanip initiative. So this requires, of course, a lot of efforts. So this is the result of the comparison with in situ observations applied to 4 LAI global products. So on the left, you have the GOV1 Copernicus product. Then you have the MODIS. Then the Cyclops and the Globe Carbon product. Well, the best for here, when you consider all the vegetation types together, the best correlation is obtained by the Copernicus GOV1 product with nearly no bias and an excellent correlation with a squared correlation coefficient of 0.8. But if you consider the forest sites alone, you see that the consistency is not that good. then this was for in situ data. Then, as I said, in situ data are limited in space and time, so it's also interesting to use model simulations driven by atmospheric reanalysis, for example, such as event-theory. So, first examples regarding surface moisture. So, in this case, we use the ISBA model over France at a spatial resolution of 8 kilometers, and we compute temporal correlations with a number of products. So, from left to right, you can see the AMSURI product, then the WINSAT product, and the ERS-SCAT product, and you can see correlation maps. So what is striking here is that the spatial features of the temporal correlation may differ sharply from one satellite to another. So, yes. In particular, the ERS-SCAT result is markedly different from the other two. Which is logical because ERS-SCAT is a radar, so it's an active measurement, while the other two are radiometers. Well, another example, so it is ASCAT and SMOS again. So on the top, you have temporal correlations between the model and the SMOS, and below you have the same for ASCAT. And on the right, you have the p-value, which has to be as low as possible. So again, now we find that over France, the ASCAT product is closer to the model simulation than the SMOS product. And this is consistent with what we got with the in-situ simulations before. So then you can have a look also at the seasonality. So this is an example based on ASCAT data. So what is shown here is the date in the year where surface soil moisture is minimum. So when the soil is the driest at the surface. So orange to yellow colors corresponds to springtime, and blue corresponds to summertime. So you can see that in the model, in general, the driest conditions are observed at summertime. But in the ASCAT product, in northern France, the driest conditions are observed at springtime. So there is a clear discrepancy between, from this point of view, between the model and the ASCAT. And if you want to do data assimilation, I will talk about that afterwards, you have to rescale the satellite product to the model. And on the right, you can see the corrected ASCAT after seasonal CDF matching, cumulative distribution function matching. Then, now an example at the scale of Europe. So again, model simulations are compared with the satellite products. So on the top here, you see the ESA-CCI product, and below you see the AMSURI product. So the ESA-CCI surface moisture product has a property to combine several satellite products, either passive or active. And in ESA-CCI, the AMSURI product is included, but it is combining with ASCAT or ERS, for example. So you can see that when you do the comparison with ESA-CCI, you get excellent absolute correlation. Well, it's a bit less for scaled anomalies, of course, because it's more difficult. You don't have the annual cycle. But nevertheless, you get very good results, except from some areas in Turkey and at the border between Iran and Iraq, where you get negative correlations. But if you consider the AMSURI product, well, the general correlation level is much lower, especially in Northern Europe. So this clearly shows the added value of ASCAT or ERS. You complete, to some extent, the landscape in terms of surface moisture in northern latitudes. And on the right, you can see a scatter plots of the two absolute values and anomaly values. What is interesting is that the negative values you see there in the ESA-CCI product are not visible in the AMSURI. So I mean, since the ESA CCI product uses AMP series, there is probably a way to eliminate these negative correlations. Then let's switch to vegetation and leaf area index. So the ISBA model again, because this model is able to simulate leaf area index. And in this example, we also use another French model called Orchidée. So from the LAI time series, you can derive the vegetation phenology, the leaf onset, and the length of the growing season. So when we derive that from the Copernicus product, we get this kind of maps. On the left, you have the leaf onset, and on the right, you have the length of the growing season. So you can see that the satellite-derived leaf onset is quite consistent with what is provided by the two models, ISBA and Orchidée. But in terms of the length of the growing period, we can see some differences, especially with Orchidée. But Orchidée is known to overestimate the length of the growing period. But even ISBA tends to provide longer growing periods in Central Europe than in the product. So this raises questions: who is right? So this was for the mean seasonality, but again we can try to look at the interannual variability. So to study interannual variability, again we can use scaled anomalies, but in this case we consider scaled anomalies for a given 10 daily period, for example, and we consider the interannual variability is from 1 year to another. And when we consider these anomalies end to end, we get this kind of correlation. So this example is interesting because it shows that if you use only one model, Orchidée, you get rather poor correlations. So if we had used only the Orchidée model, we would have said, well, this GOV1 product is rubbish because it's not able to provide the interannual variability. So this shows that it is important to use several models when you compare with model simulations, because with ISBA we get, at least over a large number of regions, excellent correlations. So this gives the path to the synergies between satellite data, in situ data, and models. So again, this is an example for surface moisture. So in this case, we compare 3 years of WinSat surface moisture with model simulations over a given site near Toulouse. And you can, so again, we consider scaled anomalies. And these circles here show seasonal scores in terms of p-value. So you can see that in general, the model simulations tend to be better correlated with in-situ observations than with the satellite. And an interesting feature also is that with the model, we don't have any missing data. And if we consider all the days with the model, we get excellent correlations all the time. In fact, the satellite products are limited at winter time because periods with the soil freezing or snow are eliminated from the dataset. This is why during these seasons the results are not significant. So in this case, the model is closer to the in-situ observation, but it's not the general case, because in the following example, where we compare the model with our 12 Mothmania stations here, with the SCAT product, and then SCAT with the model and with in-situ observations, we see that in general the best results are obtained when we compare the satellite product with the model. So in general, the model tends to be very close to the satellite, closer than to the in-situ observations. So, well, how to make the difference between all these results. So there is a technique which has been used a long time in oceanography, which is called triple collocation. So I will present the equations here, again in the context of scaled anomalies, because the equations are very simple in this case. So for example, let's consider 3 scaled anomalies of surface soil moisture over France. One derived from ASCAT, one from SMOS, and one from the model simulation. We can assume that the observed anomaly is equal to the true scaled anomaly, which is unknown, plus a random error. So if we write the equation for ASCAT, this is what we get. Same for SMOS and same for SIM. Of course, the true scaled anomaly is the same in the 3 cases, because the 3 products are supposed to provide the same, to represent the same true value. Then this unknown theta term can be eliminated by subtracting the equations one by one. And after doing that, if you multiply the different terms one by one, and if you do the average, you get the following equations with a number of terms. So the first term here is a mean square error for ASCAT, and then you have covariance error terms. But if you assume that the 3 quantities are independent, then the error covariance will be equal to 0. And then you can neglect these covariance terms, and you get directly an estimate of the mean square error. And of course, you can repeat the same for SMOS and for the model. So this is a very interesting technique, but it depends on this assumption that the 3 quantities are fully independent. And in fact, in practice, what happens is that if this hypothesis is not satisfied, then you may get at some places negative values of the mean square error, which of course should not happen. But this is a sign that maybe the data sets you consider are not independent. But in this case, we can consider that they are really independent, and these negative values never happen. So this is what we get in terms of mean square error for the model, for SMOS, and for ASCAT. And below you see the average value. Then another possibility is to use data assimilation. So this is an example when we use again the ISBA model. So in the land data assimilation system, you have 2 components. You have a forecast component and an analysis component. The forecast component is driven by an atmospheric forcing, an atmospheric reanalysis, in fact. It could be irradiating, for example. And then by a number of information about the surface, like a land cover map, for example. And then the analysis component uses satellite observations. Why? So in this case, it is LIFA index and surface soil moisture at the same time. So in the forecast component, there is an observation operator which you can use to go from the model state variables to the observation space. And then from this quantity, you compute innovations, and then using the Kalman gain, you compute increments. And then after all this processing, you get analyzed variables. So in this case, we assimilate LAI and surface soil moisture, and we get analyzed LAI, soil moisture, but also FAPAR and surface albedo. And this is what we get on average over France. So in green, you have the GOV1 Copernicus LAI products. In blue, you can see the model open loop simulation without assimilating any observation. And in red, you have the result of the assimilation. So you can see, yes, that the assimilation tends to shift a little bit the vegetation cycle, of course, towards the observation. The same is done for the root zone soil moisture at the scale of France at the same time. But, as I said, the model is able to provide a number of quantities like FFR and surface albedo, and these quantities can be compared with satellite observations. So this is for FFR. So you can see that at summertime the agreement is quite good. At wintertime it's more difficult. The model tends to overestimate to large extent, to underestimate, sorry, to large extent the observed FFR. But regarding FFR, there is a number of definition issues because in the observation it is always a direct FFR without clouds, which is not the case. And this is for surface albedo. So at the scale of France, so these spikes you see there are related to snow events, to large scale snow events in France. And you can see them in the observations also. And in fact, we were quite surprised to see that, well, at the scale of the countries, the agreement between the model and the observation is not that bad, including in terms of interannual variability. It was a surprise for us. So, then, well, you get these statistical quantities, spatial quantities over France in this case. So on the left you have average values from 2008 to 2012, and on the right values obtained for last year, 2013. So you see the increments which are produced by the assimilation. So from left to right, the LAI increments, the root zone soil moisture increments, and then the impact this has on evapotranspiration and drainage. And you can see that in 2013 something strange occurred, because we got very high values, very high positive values in July and August for the root zone soil moisture increments. And this is equivalent to irrigating the whole country during 2 months. So this is not realistic at all. And this shows that maybe we have a problem in the SCAT product. And indeed, you can see on the figure on the right that the surface soil moisture derived from the satellite observation tends to be very high, higher than during the previous years in 2013, whereas 2013 was very, very dry at summertime. So this shows that our land data assimilation system was able to identify a shortcoming in the satellite product. And of course, well, this was communicated to the producer of this product, and corrective actions will be taken. Okay, so I've reached the conclusion. So in situ data, they are needed, of course. We cannot do without them, but they are not sufficient. Well, the analysis of the temporal variability is not easy, and addressing the seasonal and the annual cycle is not sufficient. You also have to deal with the day-to-day variability for surface soil moisture, and with the year-to-year variability for 10-daily leaf area index or soil wetness index. And I strongly recommend to use scaled anomalies to do this work. And then, well, I hope I was able to show that it's possible to go from unapparent truth to error assessment using triple or multiple collocation. And then for cross-cutting quality monitoring, one can use data assimilation and reanalysis. Is a powerful tool to assess the quality of the upstream products. So I would like to acknowledge a number of funding sources and projects which contributed to the results I just presented, both at the national level and at the European level. And then I added a number of references for further reading related to soil moisture, differing depths, and triple collocation and data assimilation. Thank you for your attention, and I'm ready to take some questions.
Questions?
Yes?
This triple co-location or multiple co-location sounds really interesting, and certainly it offers a lot of possibilities. But how do you feel that if you have several data sources that have about similar error sources, is it possible that they start to dominate the result? If you have one which is very different from the others, and let's say you have a family of satellite datasets who are about the same, how do you feel about that?
Well, yes, thank you for this question. Well, again, a condition for these methods to work is that the error associated to the considered variables have to be completely independent. Well, the quantities have to be completely independent. If this is not the case, this method cannot work. For example, if you use two model simulations in this kind of methods, you are bound to have negative mean square errors. But at the same time, if you get at some places negative root mean square errors, sorry, this is a sign that your method is not working. So you have a kind of diagnostic that the method is not working.